Thank you for introduction. Welcome to my talk. In this talk, I'm going to introduce our new work on verification of RCU under relaxing memory using separation logic. Concurrent programming is hard to get right. For instance, here's a bug report from a popular ROS concurrency library called Crossbeam. It describes a user after free error in their concurrent lock-free queue implementation. It turns out that this bug was caused by misusing a memory reclamation library called RCU. We're not going into the details of this bug, but the takeaway is that memory reclamation adds another layer of complexity to concurrent programming, which is already complex enough. So our aim of paper is to tackle this challenge by providing a formally verified foundation for using and implementing RCU correctly. To understand RCU, we first need to see why memory reclamation is a problem under lock-free concurrency. Lock-free algorithms share data without acquiring locks to avoid contention. This is great for scalability, but it creates a problem for memory management. For example, let's consider a shared data structure with a root node and a data node n. Suppose thread 1 is reading the node n. But at the same time, another thread concurrently removes that node from the data structure and frees its memory. Now, when the thread 1 tries to access n, the program will crash due to the user after free error. So to prevent this kind of error, we should ensure that we defer the reclamation until all threads are done accessing the memory for the node n. And RCU is a popular solution for this problem. In RCU-based system, we should activate a RCU critical section before accessing the shared data. This critical section doesn't really lock the data, but it protects the data from being reclaimed. And on the other side, after we detach a node, we should call the retire function instead of directly freeing it. This function tells the RCU system to reclaim the node later when it's safe. The actual reclamation will happen only after the critical section are deactivated. So with the basic idea of RCU, let's revisit the bug from the first slide. The original bug is quite complex, so we're going to use a simpler example that shows the same underlying problem. Now let's imagine two root nodes pointing to a node n. We want to remove the node n from the data structure. So we first cut the link from root 1 to the node, and we make a critical mistake here. We forget to cut the link from root 2, and then we just retire the node n. The problem is that RCU fully trusts you, and it sees no one is in the critical section, so it decides that it's fine to free n. But as a result, the pointer from this root 2 is now a dangling pointer. So if someone follows this pointer, it will cause user after free error, even if the thread is inside the critical section. So this bug highlights a requirement of the retire function that the node to be retired must be completely unreachable from the roots. And our question is how to enforce this kind of requirement. Actually, this is the problem we already explored in our prior work at Uppsala 23. In that work, we used a concept called the pointed by assertion. This is basically the reverse of the standard points to assertion of the separation logic. So for example, in this case, we simply have root 1 points to n and root 2 points to n. And on the other side, we have the pointed by assertion that tracks all the incoming pointers to n, which are root 1 and root 2. Now suppose we cut the link from root 1. Then our pointed by assertion is updated to just root 2, removing the root 1. And if this pointed by set becomes empty, we know that the node is now unreachable. So this means that we can use the empty pointed by assertion as the precondition for the retire function. In the current state, we can satisfy this precondition, so it's verified that it's safe to retire n. But in the bug example we saw a while ago, the root 2 is still inside the pointed by set. So the proof is going to fail, which means that we're going to catch the bug while we're trying to prove the code. So our verification worked pretty well, but the limitation is that we assume the sequentially consistent memory model, or simply SC. In SC, memory operations are strictly ordered. But the problem is that modern processors and compilers don't provide SC by default because SC incurs a lot of overhead. For maximum performance, they use relaxed memory consistency, or RMC. But RMC has serious implications for our verification method. One issue is that the pointed by assertion becomes dependent on the view of each thread. Let's see an example. Suppose we have a link from root to n, and we cut the link by writing no to the root. But in RMC, this write doesn't immediately propagate to other threads. So it means that the other thread may read the old value, the pointer to n. Which means that, so while some thread, that the thread that cut the link thinks that n is pointed by nothing, another thread may think that n is still pointed by root. Then our question is, what's the meaning of the pointed by assertion under RMC? This brings us to our improvements to RMC separation logic. First, to verify the uses of RCU, we designed the pointed by assertion that works correctly under RMC. And in addition, in the later part of the talk, I'll introduce our work on verification of RCU implementations. For this task, we made a new proof rule for a crucial synchronization primitive called the SC fence. Let's dive into the first contribution. So we want to build a new pointed by assertion. But to do that, we first need to see how the existing RMC logics handle the points to assertion. Since in RMC, it's possible to read the old values, the points to assertion now has to track the history of the values written in the location. We can think of this history as a simple list. For example, suppose the node initially points to n1, and then we write n2, and then n1. Then the points to assertion of the node R is going to be list of n1, n2, and n1. Now, let's build the RMC pointed by assertion. We're going to do this in 2 steps. So we're going to first track the old edges, including the stale ones, and then we're going to hide the edges that are observed to be stale. For the first step, we need to identify each edge, and we're going to use the identifier as the pair of the source node and the index of the pointer value inside the points to history. And then we're going to build a set of all incoming edges, which is going to give us n1 pointed by r,0 and n1 r,0 and r,2, and n2 pointed by r,1. The second step, we're going to hide the stale edges. So our end result should be that the pointed by set of n1 should be just r,2, and for n2, it should be empty. And the question is, how do we justify deleting the old edges r0 from n1, r0 from n1, and r1 from n2? The key idea is that the overriding thread that wrote the newer edges know that these values are stale because they observed that the new value they wrote. We can model this observation as the scene assertion, which is already provided by the existing RMC logic. For example, by providing scene r,1, we can delete r,0 from the pointed by set of n1, and then with scene r,2, we can delete r,1 from the pointed by set of n2. So that's how we made RMC pointed by assertion. Then how does this apply to RCU? Well, it's basically the same as the essay version. That is, we use the same proof rule as the same proof rule for the retire function, except that it uses the RMC pointed by assertion under the hood. So that's how we adopted the pointed by assertion of RMC and how we verify the RMC usages. Using this, we verified some log-free data structures that use RCU, including the fixed version of the queue that appeared in the bug report we saw at the start. Now, let's take a look at how to verify RCU implementations. So this is the RCU implementation we verified. This is rather complex, so we are not going to the details, but instead, let's focus on this highlighted part. In this part of the code, we first write to a shared variable, and then we execute an instruction called scfans, and then we read another shared variable. Because of this pattern, we call this pattern read after write synchronization, or simply raw synchronization. And this pattern is essential for RCU and many other concurrency algorithms. To understand how raw synchronization works, let's look at a simple classic example. This simple code snippet implements mutual exclusion for two threads. It uses two variables, L and R, both initialized to 0. The left thread writes 1 to L, and the right thread writes 1 to R. And then they read the variable written by the other thread. If they read 0, they enter the critical section. In SC, we can see why this works by a case analysis on the order of these two writes. We can see that in both cases, at least we know that at least one thread ends up reading the value 1 written by the other thread. This means that no more than a single thread enters critical section, which implies the mutual exclusion. But this property breaks in RMC because there's no strict order between two writes. Specifically, it's possible for both threads to read the old 0 values. So these both threads could end up reading the old value 0, and they could enter the critical section, which violates mutual exclusion. To fix this problem, we must insert the scfans instruction between the write and the read. These scfans instructions have a global strict ordering, and they propagate the preceding write to the thread that runs the later fences. We can see this adding fences restores mutual exclusion by a case analysis on the order of fences. Let's say the left fence executes first. Then because of the fence synchronization, the write to L becomes visible to the right thread. So the right thread must see the value 1, which blocks it from entering the critical section. And the same reasoning applies to the case in the symmetry case where the right fence runs the first. And our new proof rule for scfans captures this reasoning pattern. The main idea is quite simple. First, we introduce an assertion called the SC hist. As the name suggests, this tracks the global history of the SC fences as a single list. This allows us to reason by the case analysis on the order of the fences. And when a thread runs an SC fence, it can add its observation of some events to this SC fence history, which is indicated by the precondition sin E in the sin E. In the mutex example, each thread is going to add the observation that they wrote 1 to their variable. And after the fence, the thread running the fence, we're going to obtain the observation of all the prior events as indicated by the sin assertion in the post condition. In the mutex example, the right fence came, in this example, the right thread fence came later, so the right thread gets the observation of the value 1 written by the left thread. Nicely, the same reasoning pattern applies to RCU implementations. In RCU, conceptually, there are fences inside the retire function, and there's another fence inside the function to enter critical section. So we can consider two cases. In the first case, if the fence in the retire function happens before the fence in the critical section, then the thread entering the critical section will receive the observation of unreachability of the node, which is provided as the precondition of the retire function. So the thread in the critical section will not be able to reach the retire node. And second, if the fence of the critical section came first, then the RCU system is going to see that there can be a thread inside the critical section, which means that the RCU system is going to defer the reclamation. So that's how we, that was our SC fence logic. Using this logic, we verified an epoch-based RCU implementation we saw a while ago, and we also verified a classic algorithm called the Peterson's mutex, which is another important example of using these SC fences. You can find the details of You can find the details of these case studies in the paper. And to conclude, we made it possible to verify the realistic RCU implementations under relaxed memory using the new pointed by logic and the SC fence logic. And finally, we mechanized all our proofs in the RAW prover and the Iris framework. Thank you for your attention, and I'd be happy to take any questions.
Okay, thank you for a great talk, and this is also a winner of Distinguished Paper Award. So, please state your name.
Oh yeah, I'm Derek Dreyer, Max Planck Institute. So this is really interesting work. So my question is, the SC. I'm particularly interested in the SC fence proof rule because that's something that wasn't supported in the previous weak memory separation logics. It's remarkably simple. So I'm wondering what is there something? I'm wondering why it wasn't developed before. Is it that the proof is complicated, or that it's a kind of low-level rule and it's harder to work with, or what's the catch, or is there a catch?
As you correctly pointed out, the proof rule is remarkably simple. But the problem is that the actually case studies are really difficult because you have to reason about this SC fence history, and you really need to consider all the cases that arise from the ordering of the fences. And the problem is that when you assume the general case where you run the API functions multiple times, which means in this case you have to consider more cases.
Okay.
So I think that's the main reason why there was no work tackling this the algorithms that has to use SC fences.
So I mean, does it force you to reason about sort of lots of different interleavings of these?
Yeah, exactly. Yeah.
I see. Okay, so it's a fairly low-level rule.
Yeah, exactly.
And another question maybe while you change, is it difficult to move to other data structures and maybe even to other reclamation schemes?
So actually we were doing another case study using, which is to verify the hazard pointer algorithms. So the proof rules are quite similar. So there are some portion of the proof rules that are shared between the RCU specification and the hazard pointer specification. So the main idea doesn't really change, but for hazard pointer, the proof gets a bit more complex because I think you already know about the validation, things like that, which is already complex even in the SC version. So and this exacerbates in RMC. So I think it's quite difficult to hide all the details like this inside RMC.